Hi everyone, today we're going to go through some basic statistics. But first let's talk about the scientific method and why we need statistics. In research, we usually start with a hypothesis, which is a statement of predicted relationship between variables. So we come up with some sort of a relationship that we think might exist. We then run experiments on that hypothesis in order to collect some data and to determine our conclusions. If you've ever read a research article, you know at the end of the research study, typically the researchers will say, and therefore we need more research to be done on this topic to find more answers or to confirm the results that we found, which then feeds back into further hypotheses. So the scientific method really keeps running in this circle of coming up with hypotheses, running experiments, getting results, forming conclusions, and coming up with new hypotheses. The first step that we take whenever we're going to run an experiment is to come up with who's going to be in our sample. And so typically what we do is we come up with, well, who's our target population? Which group of individuals are we wanting to be able to generalize the results to? But then we have to realize that not everyone's accessible within that target population. And so we realize we have to go with the accessible population, which means that they fit designated criteria like our inclusion and exclusion criteria, and subjects that are accessible as a pool of subjects. I know a lot of times with clinical trials, we have subjects coming in multiple times a week. Not everybody is capable of doing that, whether it's transportation, work obligations, family obligations, or they just don't want to. And so our accessible population is sometimes different than the target population. But really, we're interested in trying to get data that can relate back to the target population. So we draw our sample from our population, and we hope that we can generalize back to the target population. So here's our population. We take a sample, we run our experiment, and then we hope that we can infer the results back to the population. This inference is why we need statistics, because we can't state that what happens within the sample is necessarily going to happen with every single person in the population. And so what we're doing with the sample data is coming up with how variable is it? How much difference is there from person to person? And therefore, can we then apply it back to the population? Can we generalize it? Can we infer these results back? One thing I do want to say is that the first step in statistics is typically a power analysis to determine the sample size. A power analysis is something that researchers do when they want to be able to determine how many people should they be pulling from a population in order to get an adequate sample so that they can then infer those data back to the population. In order to determine a sample size, there's a few different key pieces of information that researchers have to have. So they have to know what power do they want the study to run under, what effect size did they have in pilot studies, and at what significance level do they want to run the experiment. And so these different aspects are plugged into an equation, which then tells us the sample size. Now, we're not going to go over what is power and effect size and significance level today, but I just wanted to make sure that you knew researchers don't typically just pick a number as to how many people should be in a research study. There's typically a power analysis in order to determine the sample size. On the right-hand side, you see that here's the power analysis, and here's the a priori power analysis. This is the gold standard. What that means is that as researchers, we should be deciding how many people should be in the study before we run the study. Sometimes you'll read that a power analysis was done post hoc. What that means is when they're done with the study, they then use the data from the study in order to determine what should the sample size have been. So they do a power analysis based on the study data after the study is complete to see was their sample size enough. That's not as ideal as the a priori power analysis. And sometimes the post hoc power analysis feeds into the next study that comes up, the full-scale study. When we talk about biostatistics, we usually talk about two different types of statistics. There's descriptive statistics, and then there's inferential statistics. Remember how there's the target population, and then there's the sample from that? And we infer the results of the sample back onto the full population. That's what inferential statistics are all about. It's really trying to develop generalizations based on the sample data back to the target population. Descriptive statistics are different. Descriptive statistics are not trying to infer anything. It's really just taking the data that were collected, using those data to describe the outcomes just based in the sample that was in the study. And so descriptive statistics are purely describing the sample outcomes, whereas inferential statistics are inferring those results back to the main population. Some of the descriptive statistics that you'll see are mean, median, and mode. These are very common terms. Mean means average, median is the middle number, mode is the most common number. You'll also hear in descriptive statistics standard deviations, which is kind of like the, we call it the measure of dispersion. So it's like the plus or minus factor. Inferential statistics is really based on what type of variable that we have, whether we have continuous data or categorical data or even binary or dichotomous data. There's many, many different types of inferential statistics. People get PhDs in biostatistics, and it's because there's so many different ways to analyze data. So what I'm showing you today are just kind of the basics, the main types of data analysis that happen. You've probably heard of t-test, ANOVA, chi-square. These are three very common types of inferential statistics. A t-test is when we have two different groups and we're just comparing the average of a continuous variable. And so we might have Group A and Group B, and Group A went on the Mediterranean diet and Group B went on the zone diet, and we're measuring what is the difference in weight loss between the groups. And so it's a continuous number that we're comparing from group to group. And ANOVA is when we're comparing continuous data averages between more than one groups. So let's say we have the Mediterranean diet, the zone diet, and the Atkins diet now. A t-test only does two groups. You can only look at two groups at once. Whereas in ANOVA, you can have three different groups with three different diets, or four, or five. And so it's just like a t-test. If you ran an ANOVA with only two groups, you'd get the same result as a t-test. We then have a chi-square test. This is comparing dichotomous outcomes between two groups. And so if we're looking at, let's say, Mediterranean and zone diet, but our outcome isn't the amount of weight they lost, the number of pounds. Let's say the outcome was, did you lose weight, yes or no? Now we could do a chi-square because it's a dichotomous outcome that we're looking at. This type of table, when I first saw it, really helped me better understand how do we know which test is for which type of data. You'll see that there's different columns. The first column indicates what type of variable are we looking at, outcome variable. And then across the top, the row is if we have two groups or if we have more than two groups. So the first row says continuous variables is our outcome. If we had two groups, we'd run, it's called an independent t-test, which means Mediterranean diet or zone diet, two different independent groups. If we add in the third diet category, now we would run an ANOVA. But sometimes we're looking at continuous variables in the same sample. And so instead of looking at how much weight did they lose in one group versus another, which is like the difference in pre-post weight, we might want to look at the same group. So let's pick the Mediterranean diet. And we want to know, was there a significant difference at the beginning, like their baseline weight, versus the end when they were done with the diet. With this type of study, where it's the same sample, we still do a t-test, but it's called a matched pairs t-test. So it's looking at data within the same group, but there's multiple outcomes. So it's usually over time. We can do the same thing with ANOVA. With an ANOVA with multiple groups, we're calling it a repeated measures ANOVA. Again, we might be looking at pre-post data in 3 different groups. So we're not comparing between groups, but rather we're comparing within the group, was there a difference from pre to post? With categorical data, if we have yes-no data, let's say, 2 groups, we do a chi-square test. More than 2 groups, we can still do a chi-square test. It's a slightly different type of chi-square, but it's essentially the same thing. Once we get to ordinal variables, where I say it's not normally distributed, remember ordinal variables are like low, medium, high, big, bigger, biggest. With those, it's a little bit different tests. Mann-Whitney-U, Kruskal-Wallis test. These are tests that you may or may not have heard of. But I put them in there because I think ordinal variables are fairly common, and I just wanted you to know that there are statistics for those types of tests. So again, these are kind of the basic measures, the common measures that you'll see in research articles. You'll also see confidence intervals. So unlike descriptive statistics with the standard deviations, confidence intervals occur within inferential statistics. It's a very similar concept to standard deviation, and it's looking at how variable is the data. And so a confidence interval is usually looking at the 95% window. And what we're saying is that in this interval of data, we're confident that the data, 95% of the data, falls within this area. And so usually we'll say, here's the mean and here's the confidence interval. Or perhaps here's the relative risk and here's the confidence interval. So we say what we think that value should be within a sample, but then we'll say, but here's the 95% confidence interval, which is the interval in which we're 95% confident the true value lies. So we think it's here, but maybe it's here, maybe it's here, maybe it's here. We're not totally sure, but we're 95% confident it's somewhere in here. We think it might be right there, but we're 95% confident it's somewhere within here. Like I said, there's a lot of different inferential statistics. We can look at ANCOVA, MANOVA, MANCOVA, regression analyses, correlation coefficients. There's many, many different types of inferential statistics. I do want to talk about regression analysis because it's something that's also very common. Regression is a higher level statistics because it's not looking at just one variable within the data or comparing two variables. Typically, multiple regression has not only the two factors, like the dependent and independent factors, but the regression analysis includes several other factors that might be confounding factors. And so those different variables, like perhaps gender or weight or age, are included in the equation statistically in order to control or adjust for that type of confounding. And so with confounding, we know that it can affect the outcome. And so there are statistical ways to analyze the data and trying to remove the confounding effect. So it's called regression analysis. And like I said, it's a higher level. There's different types of regression. There's linear and there's logistic regression. I'm not going to go into fully how these two different types of regression analyses are calculated. But what I would like to explain is that in logistic regression, we're looking at a dichotomous outcome. And so you'll see here that the predicted y, which is the outcome, lies within the 0 and 1 range. So see how this curves? It's not a straight line because the true value can only lie between 0 and 1. This might be like yes and no, healthy, sick. Whereas with linear regression, the predicted outcome, or y, can exceed the 0 and 1 range. And so it's really pretty much anywhere, y can equal anything. So linear regression is looking at continuous variables as the outcome, whereas logistic regression is looking at a dichotomous or binary outcome measure. All of the inferential statistics will have a p-value associated with it. The p-value indicates if the outcome is statistically significant. So statistical significance determines whether a hypothesis about the distribution of one or more variables should be rejected or accepted. So remember in the beginning with our scientific method, we come up with a hypothesis and then we do experiments and we collect the data and we analyze the data. We then have to look at the data when we're analyzing it to determine should we accept that hypothesis we came up with or should we reject it? And the way we do that is based on the p-value. So even though there's many, many different types of statistical maneuvers that are out there, different ways to analyze data, we can bring it down to the p-value to determine if it's statistically significant or not. So it's very important that you know p of less than 0.05 means statistically significant. So here is a figure. If we're looking at weeks to follow up, comparing that to the bothersomeness score with 3 different groups, booklet, chiropractic, physical therapy. Here's the baseline. The p-value is not less than 0.05, which indicates there were no significant differences at the start of the study. This was probably calculated either based on an ANOVA or a regression analysis, this p-value. When we get to 4 weeks of follow-up, we can see that the triangle and the circle, which is chiropractic and physical therapy, appear to be statistically significantly better, I should say, because the bothersomeness score has dropped more than the booklet group. And so this, we're looking at statistically significant difference. Again, we're looking to see, are there group differences in the continuous variable? So it would be an ANOVA or a regression analysis. Now, if we were looking at just the booklet baseline versus the booklet at 4 weeks, that we might be doing a repeated measures t-test or a paired t-test. So what we can do is we look at these p-values along the way. We see that at 12 weeks, there's almost a significant difference. At 1 year, there's no longer a significant difference. 2 years, no significant difference. So it looks like Freddie Mercury might be happy about this week 4 p-value. One thing that's different when clinicians read research articles than when researchers read research articles is researchers are typically looking at statistically significant differences, whereas clinicians are looking for clinical significance or clinically significant differences. Really, clinical significance can be more important than statistical significant differences. So in that previous example, we were looking at a p-value of 0.06. That's not statistically significant, but it's really close. And so clinically speaking, if you're looking at what helps back pain after that number of weeks, even though it's not statistically significant to the letter of the law, clinically, you might say that chiropractic or physical therapy is more worthwhile, clinically speaking, than a booklet on how to improve back pain. So clinical significance, again, we might be, let's say we're looking at a research article where somebody's moving their shoulder. There's different treatments for shoulder range of motion. And we find that the new treatment is statistically significantly better than the old treatment for increased range of motion. Statistically, that sounds great. But clinically speaking, it can only increase range of motion by, let's say, 5 degrees. Even though there's a statistical difference, clinically speaking, does that matter? Finally, I want to say that because we're inferring data results from the sample population to the target population, there can be errors. And so if we're looking at the difference between the measured or perceived results of a study, let's say in the sample, versus the reality of what's in the target population, we can get type 1 or type 2 errors. With type 1, this is looking at a false positive. And so we measure that things are true, but in reality they're false. Whereas we can get a type 2 error when we're measuring in our sample false, but in reality things are more true, more likely to be true. Type 1 and type 2 errors are sometimes difficult to determine. We can theorize that there's type 1 and type 2 errors, but it's difficult to know unless we do further studies on larger populations or different populations. If you have any questions, please feel free to let me know. Thank you.